Assalamualaikum and good day. I be to Dr. Muhammad ARIF SAZALI and friends. Today, our group, which is Group 1, are going to present on Lab Report Experiment 7, Estimation of Heat Capacity and Entropy Generation. Our group consists of 4 members, me, Aliana Soha binti Muhammad Nasir, Nur Farisha Ildina binti Muhammad Farid, Nur Izzatul Najla binti Muhammad Razif, and Putri Nur Emilia Roslina binti Muhammad Rosli. For the introduction part, heat capacity is a physical property of matter defined as the amount of heat to be supplied to an object to produce a unit change in its temperature. Heat capacity, often symbolized by capital C, is a property that determines the change in temperature of a system for a given amount of heat supply. It is measured by using various types of calorimeter. Determination of a system's heat capacity is largely dependent on entropy when examining the concepts of thermodynamics. And this essence arises from the inherent relationship between entropy, which is a measure of heat dispersion, and heat capacity, which is the capacity to absorb heat in relation to heat transfer. Understanding the energy transformations and also distributions in engineering process such as heat sink, thermodynamic process, and heat exchanger design requires an understanding of both entropy and also heat capacity. Both of these are fundamental features that rely on variables such as temperature, volume, and mass of the system. The objective of this experiment is to estimate the heat capacity of different metals provided, and also to estimate the entropy generated when these metals are dropped in a container containing of water. For the scope part, we are using different types of metals which consist of aluminium, copper, and iron. Then, the temperature of hot water will be limited to 80 degrees Celsius only. And also, the temperature reading are recorded after each 10-second interval.
So the theory, specific heat capacity is the amount of heat required to raise the temperature of substance by 1 degree Celsius per unit mass. The amount of heat released by the warmer body matches the amount of heat retained by the cooler body when two bodies of different temperature exchange heat and intermediate equilibrium temperature is achieved. This is proven as long as no heat is lost to the environment. In this experiment, a heated solid with known mass and temperature is dropped into a calorimeter with cold water with known mass and temperature M2. The temperature at equilibrium is then measured. The quantity of heat received by water must equal to the magnitude of heat lost by solid. So this equation that we obtain is heat lost by the solid is equal to MCP, T2 solid minus by T1 solid. Heat gained by water is equals to M2 Cp T2 water minus T1 water, and Cp water is constant, which is 4.187 kg over kg Kelvin. The change in the system's internal energy is delta U equals to Q minus W. According to first law of thermodynamics, Q is positive when heat enters the system, and W is positive when the system does its work on its surrounding. In a adiabatic process, the system does not change heat with its surrounding, so Q equals to 0. And in adiabatic expansion also, the internal energy decreases. It refers to drop in temperature. According to second law of thermodynamics, a process must always occur in the direction of increasing entropy, which is Sgen more or equal than 0. Because process can occur in a certain direction, not in any direction. In this experiment, the direction of process is heat energy is transferred from high to low temperature body. Entropy generation refers to increase in entropy in a system due to irreversibility. The second law of thermodynamics dictates that entropy tends to increase in an isolated system. A system's or its surroundings entropy change might be negative, but delta S total, which is total entropy generation, is positive. The process must progress in the direction that is consistent with its increasing entropy, which is Sgen more than 0. Entropy generation measures the magnitude of the irreversibilities present during the process. In this experiment, the direction of process heat energy is transferred from high to low temperature body. The entropy created during this procedure is calculated as follows, which is delta S is equals to MCP ln T2 over T1. So delta S total is equals to delta S metal plus with delta S water. I will proceed with the experimental setup. So in this experiment, we use metal string thermometer, 3 different metals which are aluminium, copper and iron, 2 beakers, water, hot plate and weighing scale.
First, record the weight of the iron block by using an electronic balance. Next, we proceed to record the weight of the aluminium block. And then, lastly, record the weight of the copper block by using the electronic balance. Next step, pour 100 ml of water into a small beaker. Next, heat up the water using the hot plate. Attach the copper block to the metal string and submerge the copper block fully in the water. Pour 100 ml of water into another small beaker and record the initial temperature of the water. Continue heating the copper block and the water until it reaches 80 degrees Celsius, and once the beaker that containing the copper block reach 80 degrees Celsius, take out the copper block and submerge into the water that already been filled in beaker 2. Cover the beaker using aluminium foil to minimize the heat loss and record the temperature of water according to the time interval until it reaches constant temperature. And the last step, repeat the experiment by using the aluminium and the iron block.
This is a table of result for this experiment where we recorded the temperature of water when different heated metals were submerged in the water with time interval 10 seconds. We also calculate specific heat capacity of metal, entropy change of metal, entropy change of water, and total entropy generated. The formula to find Cp of metal is mass water multiplies with Cp water multiplies with T2 minus T1 water divided by mass metal multiplies with T2 minus T1 metal. For example, for copper, Cp equals to 0.1 times 4.187 times 32 minus 28 over 0.1209 times 32 minus 80, and then we will get 0.2886 kilojoule per kilogram Kelvin. For aluminium, its Cp is equals to 0.8015 kilojoule per kilogram Kelvin, and for iron, the Cp is 0.2913 kilojoule per kilogram Kelvin. And for entropy changes of metal, the formula is delta S equals to mass metal times Cp metal times ln T2 over T1. So for copper, the delta S is 0.1209 times 0.2886 times ln 32 plus 273.15 over 80 plus 273.15. Then we will get negative 0.005097 kilojoule per Kelvin. And for aluminium, the delta S that we get is negative 0.004464 kilojoule per Kelvin. And for iron, we got negative 0.004450 kilojoule per Kelvin. For entropy changes of water, the formula is similar with entropy changes of metal. It just we use water instead of metal. The formula is mass water times Cp water times ln T2 over T1. So for copper, we got 0.005525 kilojoule per Kelvin. For aluminium, we got 0.004838 kilojoule per Kelvin. And for iron, we got 0.007578 kilojoule per Kelvin. So for total entropy generated, we use entropy changes of metal plus entropy changes of water. So for copper, we got 0.000428 kilojoule per Kelvin. For aluminium, we got 0.000374 kilojoule per Kelvin. And for iron, we got 0.003128 kilojoule per Kelvin. For discussion, the question asks to compare estimated heat capacity with literature or existing data. which means we have to find the percentage error. So the formula of percentage error is equals to CP experimental minus CP theoretical over CP experimental times 100. So for CP theoretical, it's a fixed value which we can obtain. So for copper, the percentage error is 33.06%. For aluminium, using the same formula, we got 11.92%. And for iron, we got quite a high percentage error, which is 53.45%. So this is the bar chart of specific heat capacity of metals. So as we can see, the highest specific heat capacity is aluminium, which is 0.8015, and following the aluminium is iron, which is 0.2913, and slightly below it is copper, which is 0.2886. The question also asks to discuss about the total entropy generated during the process. Total entropy of a system can only increases or remain constant in any process and never decrease in value. If there is no net change in entropy, the process is reversible. Increases entropy changes indicates irreversible process. Since we obtain positive value for the entropy change from our calculation, it shows that there are some errors occurred as we supposedly obtain no net change in entropy as it is reversible process. This process is reversible as thermal equilibrium between water and metal will occur, hence the metal can be heated repeatedly. There are three sources of error that may affect our experiment result. The first one, parallax error, which is error while taking measurements such as thermometer readings. The second one, the beaker is not isolated, resulting in heat loss to surrounding. And the last one, volume of water may not be accurate as measuring cylinder was not used during experiment. So the method to minimize the error, the first one is ensure eye level is perpendicular to the scale before measuring. Second one, ensure the beaker is isolated. And the last one, use a measuring cylinder to measure 100 ml of water before transferring into the beaker. Next, justification on the importance of stirring the water in the container. While the metal is submerged in the water, it is compulsory to keep stirring the water during every significant second to ensure the heat from the metal is evenly distributed throughout the water in the beaker, hence improving efficiency of heat transfer while minimizing the error occurred. Next, justification on the importance of transfer the hot metal quickly into the water. The heated metal earlier has higher temperature compared to the air surrounding as soon as it is taken out from the beaker. Hence, heat transfer will occur to reach thermal equilibrium since there are two bodies in contact with each other and can freely exchange energy, which we want to avoid as it may affect our result. By transferring the hot metal quickly into the water, we can minimize heat energy loss to surrounding, which will increase accuracy in the value that we obtain.
For the conclusion part, we know that the heat capacity of aluminium block is the highest, which is 0.8015 kilojoule over kg Kelvin, while the lowest heat capacity is the copper block, which is 0.2886 kilojoule over kg Kelvin. For the overall entropy, we know that the iron block has the highest entropy, which is 0.003128 kilojoule over Kelvin, while the lowest entropy is copper block, which is 0.000428 kilojoule Kelvin. The estimation of the heat capacity and entropy generation experiment provide valuable insights into the thermal properties of the material under investigation. The method employed allowed a true analysis of heat capacity, indicating the amount of heat required to rise the temperature of the material. The result highlighted variation in heat capacity among the tested material, which is iron block, aluminium block, and copper block. shedding light on their ability to store the thermal energy. We can conclude that the metal has a huge difference between theoretical and experimental value of the heat capacity due to the environmental error, parallax error, and etc. The percentage of the error take place in this huge difference as we can see in the calculation. The value of the total entropy generated for each metal block greater than 0, which prove that the process is irreversible. The safety procedure of this experiment is, first, make sure the position of ice is perpendicular to the thermometer reading to avoid parallax error. Next, wear heat-resistant glove while handling the hot beaker. And the last one, stir the beaker carefully using the thermometer to get a consistent heat distribution.
So these are the references that we obtained to do this lab report.